Turn down the light. Slightly better. Okay. All right, let's get started today. What we're going to do today is lecture, as we actually will go into the theory about rubber elasticity. So last lecture, we kind of explained the difference between entropic contribution and entropic contribution to the elasticity, right? We have discussed how the spring you typically have in your ball pen is purely rely on the entropic interaction, where when you change the molecular and atomic distance between all these atom crystals, they tend to relax back to where is preferred location, just resulting changes in entropy. Okay, that's responsible for this elasticity. And for the rubber, it's totally different. So we kind of started the lecture by explaining how can we use some simple concepts, entropy terms, as well as how can we use the first and second thermodynamics to link how does the force relate to the entropy. And at the end of class, we came to the conclusion you can actually relate this term. Your force can be linked to entropy, partial derivative of the length or displacement of your material, as well as entropy, partial derivative of displacement. And all these are at a constant pressure and temperature, so we don't need to worry about the rest of the term that show up. So today's lecture going to be fun because we're going to be talking in more detail about how we can actually use this very simple equation together with single chain statistics we learned in the chapter 7 and come into a conclusion about these cross-link density and how they affect the modulus of your material. So let's get started. This particular equation we're going to use quite a lot throughout the lecture, so let me put it down here. How does the force link to different partial derivative of entropy L at P T minus T S Well, we will discuss in a moment how do we understand the partial derivative of entropy versus L, or displacement, and entropy partial derivative of L, displacement. Okay? So that's the goal of this class. So at the end of this class, the goal is for you guys to understand how can we use a single chain Gaussian coil we learned in the first part of the lecture to this particular force. Okay? And then you can predict what's the modulus of your material, etc. So, as I already mentioned several times, that our material, for polymeric material, they deform very differently with metal. And the metal is already mentioned what's the entropy and entropy contribution. So in the polymeric material, we typically assume the entropy is little change, so it will not take into consideration a large degree of strain. Okay? This is a very nice curve. We plot it as stress. Everybody understand this, right? And elongation, or this is basically a lambda. Stress, elongation, you can get this particular curve, which is shown in this curve. And this shows you what's the typical mechanical response of your rubber band being pulled. We can deconvolute this into two parts. This is basically has a contribution from entropy, although it's very low, but we cannot totally neglect it in a real case. So if you pull a real rubber band, you always have a little bit entropy change while you're pulling apart it. But it's more or less constant, as you can tell. And the entropy contribution is proportional to the elongation. We will come into this in a second. And this line with the circles are plotted as the entropy contribution, which is exactly the second term we just wrote here. Okay? Entropy contribution. So the point for this curve is, we need to consider in the entropy contribution, but it's little. So why don't we, for the simplicity of discussion today, came up some concept called ideal elastomer. We're going to talk about. We also assume your deformation of molecular level matches with your macroscopic, so also called a affine model. Okay, so your local distribution will match your global changes. So this simplifies the problem a lot. Why? If we assume there is no entropy come into play, then your force is strictly only related to the entropy change during the deformation of a polymer chain. Right? So if we can calculate the entropy, if we know S, then we can calculate what would be the force. And you can get the force L curve, which now can predict the mechanical property for an elastomer. So now the question for you guys is, how can we get the entropy of a change for a polymeric chain before and after deformation? Somebody help me? Max-Boltzmann distribution. How does it link to entropy? Give it a little more detail, Sam.
Entropy is just a measure of the number of microstates. So you know the final number of microstates and the initial number of microstates. You can calculate entropy. Generally, you can use the Boltzmann distribution.
So
you can use chain conformation.
So what Sam suggested is, if you know what the entropy before you deform a polymer chain, and you know the entropy after you deform the chain, you should be able to calculate out what the entropy change before and after you stretch a rubber band. And if we knew that, we can basically apply this very simple equation. Assume this is the ideal elastomer, take away this entropy term, and use this as an approximation to calculate out. Because L is we know exactly, so that's the point of this today's class. We're going to use this approach to calculate out what is entropy for the deformation of the polymer chain. Okay, there's a little bit equations come into play, but I think everybody can handle that compared to what we have go through lastly. Okay, so this slide we'll talk about the a concept called thermoelastic inversion. This is actually a lot of professors like to talk about in rubber elasticity. They like to do a demonstration and ask a student to follow it. So what typically do is, in a case, if you hold a rubber band in your hand, if you stretch it very rapidly, and there's changes in temperature in the rubber band. Because you can think about the case, when you deform it, the rubber band will lose entropy. So it will need to take some forms of work from the environment. So it will give out heat, actually. And if you let it go, the rubber band in the stretched state, and it will relax back, but at the same time will take some heat from the environment. There's a tiny little bit of change in temperature. We are talking about less than a degree is probably, but if you put into some sensitive part of your body, you can really sense the tiny temperature change. Not by my skin, but actually close to your lip. It's mostly sensitive skin, and if you pull a rubber band, go back and forth, you can sense it's going through the heat and the cool cycle. Okay. This is a general truth for a large degree of strain. So if you pull the rubber band from a little bit to a lot, it's very obvious. But there is one concept I want to introduce you guys is at a little bit deformation, your thermal expansion will dominate, and you wouldn't have actually see that phenomenon. So as shown here, which at different cases where you can see at different temperatures with different strains, your stress actually would go through a slightly different phenomena. Okay, this is not exactly as we stretch it, but in this case, what they measured is measure the stress and over a different temperature. So how do they perform this measurement? Is they pull a rubber band through an instron. If you put a clamp there on each side, if you pull the rubber band, you're going to start to apply some of the stress into the clamp on both sides. The more you pull, the larger you would have stress applied to your material. Now imagine we hold this clamp and start to vary the temperature to this clamp. You put an environment chamber. As we mentioned, that a phenomenon between the difference between the metal and elastomer is when you heat the elastomer up at a constant weight, it will retract, right? We have talked about that. So that is due to the changes in the changes in the modulus of your elastomer. Your modulus would go up. Your rubber will get stiffer the higher the temperature. So that's why you typically expect an increase in the stress with increase the temperature. As you can see, 13, 20, and 38 degree of strain is more obvious. But what scientists also found is at low degree of strain, this was not so obvious. And this concept is called thermoelastic inversion, and this is purely due to the thermal expansion. Okay? So in today's course, we're mostly going to focus on those high degree of strain. Okay? Above this, 3 to 6%. And that's not the region we should worry too much. Everybody got this part? Now going back to the concept about the entropy. We're going to talk a little bit about single chain entropy. How do we discuss the entropy change before and after stretch? And this is kind of a flashback to the first lecture we did. Everybody recall this equation for the Gaussian distribution of the single chain in the bottom part. So you have a probability of the chain and distribution at different degree of at different r distance. So this is showing if you fix of the molecular origin, one end at molecular origin and the other end freely, and you can calculate what's probability you find the polymer chain end at the distance of r from the origin. Okay, the probability is inverse proportional to the r, and mb squared is basically end-to-end distance for the Gaussian core. So, and everybody recall, we also talked about entropy of distribution from the Flory-Hagen theory, where we have entropy would be proportional to potential possible state of your polymer chain, right? So your S will be equals to K ln delta. And if we know these two equations, we actually can apply those two concepts to trying to get the single chain entropy before and after we stretch it. The number of states will be proportional to the probability, because probability only tell you what it would be the possibility of reach there. But if you apply this k log lambda, so this would be representing a constant multiplied by p and r. This would give you the final possible of state. Okay? So we can basically apply these two together. As we explained here, in the early days, the theory of rubber elasticity is really based on statistics. So in the early days, this is done by Wall and Flory, as well as Rayner. So those three scientists that developed the fundamental concepts of how to deform a polymer chain. Again, we will talk about a few ideal case. Okay, like we talked about the ideal elastomer, we didn't consider the entropy during the deformation. There's a few more notions we need to learn. First, called affine deformation. Everybody can guess what this means, affine deformation? What would be the affine deformation? Means when you deform something.
Like
Master?
the ability of the structure
Mm-hmm.
for yielding or deformation for fracture.
Yeah, but not exactly in this case. Affine in this particular case is we are trying to link a molecular level of change to macroscopic level of change. So let's say if your polymer, if you pull some kind of plastic, they would yield and they would form a neck. So your deformation is not uniform throughout the sample. Some area is not deforming, but the necking area actually being stretched a lot, right? So this is one of the case only. So, but affine model specifically means whatever happens molecular level follows macroscopically. Okay? Let me repeat again. Affine model basically says what happens at molecular level agrees what happens macroscopically. So like yesterday, if I stretch a rubber band twice of the length, it sinks at the molecular chain. It's also deformed twice the length. So they agrees. It's like something is attached to a spider network. If I pull the polymer, everything in the macroscopically would increase the twice the length. Okay? This turns out to be critical to develop this ideal rubber elastomer theory, and you will see why this is important. As well as the chain segments between the crosslinks would obey the Gaussian statistics. So in the rubbery, or this is a little bit simplified, but you can think about these are crosslink points. And I'm kind of drawing this quite simple, but actually what the rubber elasticity theory states is between each cross-linked point, your polymer chain will be a Gaussian coil again. If this is long enough, this is definitely valid. You can think about the cross-link. The molecular weight between the cross-links can be up to a few thousand kilodalton, right? So for these, you can think about they can actually behave like a Gaussian coil, which means the end-to-end distance will be equal to nb squared, or how the length changes over the molecular weight. The initial network is isotropic. You don't want any preference orientation because otherwise it does not follow the Gaussian coil assumption. The Gaussian coil means it's isotropic in all direction. And last is most important is volume remains constant during deformation. This is mostly true because for rubber bands or elastomers, we know the Poisson ratio for ideal elastomer should be 0.5. That means your volume is incompressible. When you deform in one direction, it will shrink in the other direction. But ideal elastomer, people actually measured for natural rubber, it's about 0.459 or something like that. It's very close, but there's a little bit disagreement, but very minor. If we use those three terms, then we can easily apply those to the entropy. This is what we have now. Your entropy would be equals to Boltzmann constant K log delta, and that's a possible state of arrangement. And we know the possibility of states, probability of n chain end has a proportion to the R. So if you apply those two together, you can get what is the entropy for your polymer. Basically, you apply this equation in here, and you can get an entropy of a single chain. So what this entropy says, what would be the entropy for my polymer chain at this R, okay? If you apply those, you can see line of this will give you two parts. This will be the 2/3, agrees with first part. And as we can see, this part, if you pay attention to what the value is there, it's 2/3, right? And you have ln 2 pi mb squared and 3. Does it depend on R? It does not, right? So that means this part of entropy is a constant. It doesn't change with degree of strain you pull your polymer chain. As you can see, this says constant for this part. And second, ln exp exponential of 3r squared divided 2mb squared. If you take a ln of that, it will give you minus 2/3 mb squared and r squared. So this part actually depends on what the r value is. So now let's try to understand. If your r goes up, how does it affect your entropy? If your chain is getting longer and longer, actually decreases. So this R will go increase, but you have a minus sign in front of it. So your entropy would decrease when you stretch your polymer chain. And how much degree of decrease is basically predicted by this equation. And we can be more specific in terms of R. We can consider changes in the X, Y, and Z direction. So if you consider changes in 3 directions, you can get what's the value for deformation of your entropy for a single chain. Okay? So the entropy change for a single chain is given by this equation. Entropy will equals to a constant, and we explain why it's a constant, minus 3kr squared. K is, we just say it's a constant value, Boltzmann constant value. R squared is what's the final end-to-end distance. R0 squared is where the Gaussian end-to-end distance. Okay? R0 squared will be equals to mb squared. So we can actually plot this out. This will tell you the longer you pull, the entropy drops. So now the question is, what would be the entropy change after we deform the chain? Not just a single chain, but before and after we deformed it, right? So we just need to define what would be the entropy before we pulled and what would be the entropy after we pulled it. So to describe the process deformation, we just need to calculate what's the deformation entropy for the network strand, that pre and after stretch. And we all know that delta S in the deformation process will be equal to final entropy minus initial entropy. And we just need to give a scenario. So on the figure shown here, looks at this curve. So imagine this would be a polymer strand. It starts from origin, goes out to the chain end here. And this would be your initial end-to-end distance R0 inside a rubber band. So imagine there's a rubber band. These are between two cross-link points. If I pull rubber band this way, this point will be start to deform to there. And we can calculate what's the entropy of this strands before we deform it and after we deform it. Okay? Any questions? Will?
Just to clarify, so the R by itself is the total distance that it could possibly be stretched, or the actual distance?
So this R is the end-to-end distance.
End-to-end distance.
Average end-to-end distance for the points between your cross-link points. Or in this case, we can just imagine it's a single chain.
Yeah.
You don't need to put too much constraint for you. You can just imagine this will be the Gaussian coil before we stretch it. Like we learned everything in the first stretch. Yeah. Then think about you are pulling the one chain and I'm holding the chain at the origin. Now it's being deformed to be longer than what it's supposed to be. And we know R0, if we know the segment and we know the individual segments, we can actually show that it's will be mb squared. R squared will be mb squared. But we can say if we pull it to double that length, what would be the entropy change? We can calculate based on this. There's some character is not showing up properly, so this should be the final. So what we want to calculate is use the delta S for the final minus what the initial. The constant will cancel each other because they were exactly the same term as shown here. So when you consider the final minus initial, this constant term will cancel each other. So we don't need to worry about that. Only thing we need to worry is basically these, what I circled here, called R squared final and R squared initial, and the rest is the same, right? So in the three-dimensional space, R squared will be equal to x squared, y squared, z squared, right? If you have three-dimensional axis, that's very easy to understand. We can apply the coordinates between the before and after. So after we stretch, we assume you have a new coordinate of x, y, z. Before you stretch x0, y0, z0. If you apply to the equation above, that's what you would get. The changes in the delta in the strain will be equal to these two parameters. Pretty straightforward, right? And recall at the beginning, we also had a fine network assumption. What a fine network assumption will allow us to link what's x value and x0 value. Because of a fine network, we know if we deform the sample in a draw ratio of lambda, we can calculate out what would be the x versus x0. So if your sample is pulling from x direction, being deformed by a draw ratio of lambda. Let's say lambda is twice of lambda 0, means your sample is twice as long. You can calculate what's x will be twice of x0. That's right? Because we kind of claim in the assumption that your molecular level will agree with your macroscopic. Now the question is, how do we calculate what's the y and y0 position? Any thoughts? If we know what these two are linked as well as z position are linked, then we should be able to resolve what the entropy change before and after we stretch, right? That's the only thing we're sort of missing here. X is already being defined because we assume the sample is stretched in the x direction. And x will just be equal to lambda multiplied by x0. Stretch your polymer twice, your network will deform macroscopically twice the length. Any guess, thoughts? Brave idea? We have another assumption, right? Let's go back. We use this assumption to get to what the entropy. Basically, we use a Gaussian chain and distribution to calculate what the S. Isotropic is also part of the reason we can get there. How about this? Can we use any useful information from this? There's no volume change during deformation. Yes, right? Because if you know deformation in one direction, assume there's no changes, what would be the changes in the other direction? Sorry, that's not going to be equivalent. Because if y also expanded to be, twice of y0, z is twice of z0, then your volume is not a constant, right? So how do we get that? So we need to use the constant volume assumption. If you increase, let me draw a three-dimensional cube so everybody sees it more clearly. If we have a cubic has been deformed to be twice the length.
I don't think that's it.
Somebody just intruded our classroom. No worry. So we know this is x0, z0, and y0. And this is our new x, z, and y. We know if we pull it at a lambda, we would deform, let's assume, if lambda is equals to 2. That means your x will be twice of x0. You have a silly putty, you pull it, not necessarily silly putty, rubber band or rubber cube, you pull it twice in the x direction. This direction will contract between the other two. And how much degree of contract is related to the incompressibility assumption? So we know in the other two directions, you absolutely need to contract at some degree to satisfy there's no volume change. Right? So that means x, y, z would be equal to x, y0, and z0. This is the volume. There's no volume change before and after stretch. So it will be uniform deformed in both x and z direction. We basically know x will be twice of x0. Y and z direction are deformed uniformly. We can assume y would be equal to z. So we can see y squared will be x0 squared as y0 squared. If you cancel all these each other, very simple. So when one direction expands twice, you have other direction will be contract by root square of 2. Or more generally, x will be always equals to lambda x0, depending on different draw ratio. And y would be equals to ln root y0. Z would be root square of lambda and z0. Okay, so that's how you can link these different directions, how x, y, z can be linked to x, y, and z0, right? Because we assume there's no compressibility. When we stretch, extend in one direction, the other direction will contract. And we can certainly apply the knowledge we learn here into these two equations and start to now get a little bit in more depth. So, like we showed there, if you have initial box, we draw it to elongation in one direction, so we know what's the relationship before and after deformation. Okay? And you can get the new relationship between all these lambda square and x square relationship. There's nothing magic here. It's basically a very generalized form. You can describe these. And if you apply all these squares into the following term, you would get a generic equation. Changes in the strain's entropy would be equal to minus k 2mb squared over 3. And x0 squared means where your initial position is. Lambda x minus 1, lambda y minus 1, and lambda z minus 1. Okay? This can be applied to any type of deformation. There's no assumption that it has to be uniaxial, but in the next step we will talk about what if it's just a uniaxial stretch, not like shear. So this would be happens if you have the whole network, and we can take a short break, then we can come back to talk about this. Okay? We can take about maybe 5 minutes, then we have 3-4 slides to summarize this. Yeah.
Is Poisson's ratio related to the deformation in the y and z directions?
Yeah. Poisson ratio definition is changes in the y and z direction with respect to x direction.
Okay. I just wasn't sure how to make that connection for that equation.
Yeah, it's not the fully related, but you will see in the next step when we explain how the delta S is changed with respect to different direction, then you will make the click, which will be the second half of the class, okay?
Okay.
Well, this may look like very busy slides, but the science in the slides is not that complicated.
Right.
Okay, so let's give it a minute or two, then we can come back. You guys must be, because we don't have class on Tuesday next week, right? Just to make sure.
We have the whole
No class? So you guys get a whole week off. Mm-hmm.
We just took our last exam of the semester today. So it'll be nice.
Nice. Okay, so let's come back and chat a little bit about how we can continue to understand this. I think everybody is excited. There's no class for tomorrow either. Oh, I'm standing behind your holiday. Ah, I see. Well, the rest of us, we have 4 slides standing between you and your holiday. 4 slides, okay? Every slide is 25% of progress. So we have talked about single chain entropy. Now, how can we understand when you deform a network? Basically, think about the rubber band where we have a lot of these individual strains fixed between 2 cross-link points. When we deform it, we can basically assume it will be the sum of all the individual strains in between the cross-link points. So the first equation looks very long. It's exactly the same as this equation, except that we now going to sum up all the individual strains, okay? All the strands are sum between these terms. So as you can see, we need to sum up all the deformation, all the ranges, and we assume there's n number of strands inside the network. And everybody understands what the strands mean, right? So how many polymer chain we can count in between any cross-link points. So these are the individual units inside the cross-link network. Well, we also made an assumption that all the polymers are isotropic. Isotropics means basically we think in the initial states all the changes in the x0 and y0 and z0 direction, or your initially, let me go back, initially it will be equal at x, y, and z. Why? Because this is isotropic, so you would have ended up end-to-end distance will be uniformly distributed around x, y, z direction. If x0 is longer, that means your Gaussian core is already elongated in one direction. If it's not elongated, it should be equal possible. Okay? That will allow us to make another simple assumption. If your initial state is isotropic, we can basically make these changes when you add up x0, y0, and z0, you would get r0 square. That's end-to-end distance in the initial states. Okay? And we can also assume the following changes. If x0 and y0 and z0 are equal, then each of them will be 1/3 of this r0 square. Okay? As stated here. Why we need to make this assumption? Because later it will become important while we calculate the density of strands. Density of strands will be critical. Looks like some noise going on. Let's close the door. So how can we further simplify this? R0 square, and we know R0 square will be always the same. And we know it needs to add up n times, or there's n strands in the system. So this will be equals to n number of strands in your polymer network multiplied by R0 square, initial end-to-end distance, divided by 3. if we apply this back to this equation above, we know what is x0 is, y0 is, z0 is. Basically, they all going to be equal to this parameter. We now can make one more simplification. This simplification basically tells you delta network will equal to minus 2 nk, and deformation in x, y, z direction square minus 3. Everybody gets why we have a minus 3, right? Because when we apply this into the first term, we can group all the x, lambda x square, lambda y square, and lambda z squares to here. And there's 3 minus 1 term can be grouped into the minus 3. N is now became the number of strands. So how many strands in the system? If you have more strands, your delta S will be higher. K is Boltzmann constant again. So I want you to take one more look for this particular equation. And the MB square here is cancelled out with R0 square. So there's no MB square is related. It's pretty straightforward. Okay? That's the delta S changes for the network system. N is a constant, okay? If your network is defined, you know how many strands of it. So if you look at this box, you can count 1, 2, 3, 4, 5, 6, 7, 8. There's 8 polymer strands inside the system. This will be a constant. K is constant, so changes in the delta S in the network is inverse proportional to draw ratio inside the system, square. So if you pull it twice or 3 times, you know exactly how much changes in terms of entropy change. Of course, sometimes people would be more accurate to replace this N as a VE term. This is equivalent called adjusted number of elastically affected strands, because we don't have a way to count strain directly because we don't know, or we don't have a microscope can look at elastomer to know what number of strands, but we can calculate out this effective strands, and we will come back to again what effective strands mean, because we can measure the modulus and come back to calculate this effective strands. Okay, we finished 25%. We have explained quite clearly how does all the lambda will be relate to each other. The draw ratio in the x direction and y direction and z direction, if we assume it's just a tensile deformation, one direction, because of constant volume constraints, all these will be equals to 1, right? Your deformation in one direction multiplied in the other direction will be 1, so there's no changes in the volume. And we can use this to get what is lambda y and lambda z, as we also discussed there. Lambda y and lambda z will be equals to, this is missing a slash, 1 divided by root square of lambda x. Any problem for this one? I want to make sure this is captured. If not, then the rest will be a very smooth downhill skiing trip.
Is this because it's isotropic?
No, it's because there's incompressibility in the system. So when we deform, the volume of your polymer or elastomer is constant. So your changes in the lambda x multiplied by lambda y multiplied by lambda z will be equals to 1. Or you can think about, let me get an eraser. There is no volume change, means let's assume it's going to be x0 multiplied by y0 multiplied by z0 will equals to xyz. That's the definition of the volume. And we know this will be equals to lambda x0. That's how we define the draw ratio. X will be equals to lambda to x0 after your deformation. Lambda is just let's put a lambda x here so you can get. It's just a draw ratio in the x direction. You can apply this is the same one to the y0 direction as well as z direction. And as you can see, this will be simplified as this equation. And these two terms can cancel out, which indicates lambda xyz would be equal to 1. Okay? And we know that lambda x, when we pull it in one direction, we know exactly what lambda x is. Then we can calculate lambda y and z. Y and z should be the same. Okay? So apply this into the delta S network we had in the last slides. We can now replace lambda x, lambda y, lambda z. What is lambda x? It's lambda square. Right? Lambda x square will be lambda square because lambda x is prime in a deformation direction. It will be just equal how much you pull. If I have elastomer, I draw it twice the length. This will be 2. Lambda y, as we show here, it will be 1 divided by lambda x. Lambda z, same. So everybody gets y. Now we get a different description of. So this is actually quite beautiful. Now we have a correlation for ideal elastomer for the entropy change and the draw ratio. We know how much entropy would change in your elastomer and how it depends on different draw ratio. Combining with this equation, anybody recall where this is coming from? Because Dr. Gu just wrote it here. Your force can be treated as simple as minus T, partial derivative of entropy, by L at the constant P and T, which is satisfied. We don't have change in temperature during the drawing, okay? Apply into the equation using the delta S we know above. We can apply this to get what would be the force. There's one trick we need to do is what is L, partial derivative L, and how do we convert it to lambda? It's very straightforward. L is related to lambda by a constant factor of 1 minus L0. So partial derivative of lambda versus partial derivative L, it just differs by 1 over L0. So if we give it a L0 in the bottom of your equation, you can basically rewrite the force can be treated as entropy change, partial derivative of lambda. And we already know what this value is. So that predicts a beautiful theory describe you now how much forces your polymer network would give you if you deform n strands of Gaussian coil in your elastomer. Force, let's see how it's proportional to. The force is proportional to L0. L0 we know like initial length. It's a constant so it doesn't change. N is number of strands. So more strands you have, it will be harder to deform. That is inverse proportional to the cross-link density, okay? K is the temperature. Oh, K is not a temperature. K is Boltzmann constant. T is the temperature, okay? Lambda is the draw ratio, so how much you deform it. minus lambda square over 1. Pay attention that it's not as linear as we would expect from the Hooke's law. Hooke's law tells you your force will be spring constant multiplied by draw ratio, but it's not, right? There's a second term come here into play, which is lambda square. Everybody knows if you take a partial derivative over here, it will become this. The constant will drop out. Lambda minus 1 will be equals to minus lambda square. Okay? Lambda square will become 2 lambda if you take a derivative of that. And 2 it cancels out with this 2 and this 2. So that's how we get the force. And now you can understand when we hand something in the rubber band string versus a metal core, if we increase the temperature, how does the force changes? The force would increase. As predicted here, force is proportional to temperature. So when you increase the temperature, the entropy is proportional to T. That's why the force goes up. Or in other words, if you hang a constant weight, your rubber band will shrink if you increase the temperature. Instead of like the entropy term in the metal case, it don't have the entropy term related to the T, so it will relax more. All right, we're halfway. What's left? This is probably the other most important slides we want to talk about. So this tells you how can we convert the force to the modulus of your rubber band string. How can we predict your modulus for the rubber band? We can get the stress. Everybody knows how to get the stress from Sergei's class, I hope, by now. Force divided by area. And we know the area is not the, it will be the area in the y and z direction. So you force divided by Lx and Lz will be equals to this equation. And force is already given in the last slide. So if we just apply this force term, Ly and Lz, we can also calculate out. It can be linked to Lx and Ly. It can be linked to Ly0 and Lz0 through the lambda term. The link between these two is basically a lambda term here, because this will be equals to Ly0 divided by root of lambda, right? So let me write one. Ly equals to Lz equals to Ly0 divided by root lambda, as we know. So you can get all these initial terms. If you multiply them together, it will be initial volume, x, y, z. It will tell you a volume. Number of strands, kt, and lambda square minus 1 divided by lambda. This is called the true stress in the deformation. We can predict it. Well, there's another term called engineering stress, and everybody knows the difference is basically a factor of draw ratio. This will be the engineering stress. Now, it's kind of very pretty. You only left 5 terms in the equation. Your stress in an elastomer will be proportional to number of strands divided by volume. We sometimes actually combine these two together, called density of crosslink, right? Giving a specific volume, how many number of strands. The more strands in the volume means you have more crosslink points. K, constant, T is constant at room temperature. So number of strands relate to how much they deform. That's how you can predict the modulus of your rubber string using very simple entropy theory and as well as the deformation. Okay. You can also get some more terms. We can, if we know the stress and we know the lambda, we can actually calculate the modulus out of it. You can apply this equation. Draw ratio minus 1 will be your strain, right? You can now replace the lambda using the strain, apply into the same equation above. You can actually get this relationship. Your stress will be equal to 3n kT divided by V multiplied by degree of strain. Stress is related to the strain by Young's modulus, so you can get the Young's modulus using the same theory. Young's modulus, as you can tell, it's a 3 times n kT divided by volume. You can also predict the shear modulus. Shear modulus in when Poisson ratio is 0.5, you can get shear modulus will be 1/3 of the engineering modulus or Young's modulus. It will be directly equal to nkt divided by V. Okay? So is that simple? Kt is constant, so your modulus is literally proportional to number of strands per volume. So if there's more cross-link points, your modulus go up. And they go up linearly with cross-link points. The second way we can represent this is using the mx term. Mx, let me explain what's the mx. Mx means instead of using number of cross-linked points per volume, we can also use the molecular weight between the cross-linked points. Okay? If your volume is constant, now think about, again, this case, we can describe by molecular weight between the cross-linked points. In this case, number of strands directly is proportional to the shear modulus. But meantime, the modulus is inverse proportional to the cross-link molecular weight between the cross-linked points.
Can this relationship work for glassy networks as well?
I think glassy network will be hard to deform. There is one assumption that when you want to deform this, you are already in the mobile state. So that's why elastomer is typically, you have Tg below room temperature, so the chain can be deformed. So for the glassy states, I think it applies, but you wouldn't able to deform it. So G would be inverse proportional to mx. So the more, it's telling you the same story. The more cross-link points n, or cross-link density, means for the given network, the molecular weight between two cross-linked points will be lower. If you double the cross-linked point density, means you add one more cross-link point there, your cross-link molecular weight is dropped by half. So essentially the same. This theory is actually very successful. So as the last slides will tell you, this is what has been predicted and measured in real world for the rubber material. So what we plot is tensile compression force or tensile force. One is where it's initially started off. This is compression, this is the extension, as we see the length. The solid curve is where predicted by the theory we have discussed. These dotted lines are basically measured in real time. We will talk more a little bit why there's deviation, as you can see, we made quite some assumptions. Incompressibility, a fine network, we will address in the last lecture after you guys come back from Thanksgiving. But the conclusion for today is, despite this is a very simple, very easy theory, but it works very well for ideal elastomer. You can basically predict what is rubber, your rubbery material's modulus. As you can see, it's inverse proportional to mx modulus. So if we know the cross-link density or molecular weight between the cross-link points, we can predict the modulus. And it's worked really well. So typically cross-linked a molecular weight between all these cross-links points are about a few kilodalton. So a few thousands grams per mole between the cross-link point. Your polymer will be much longer than that for the elastomer. Natural rubber, it can be hundreds or thousands kilodalton. And now you throw in the sulfur, you vulcanize them, you cross-link them. So a polymer chain typically has, many cross-link points along it. It's segregated into individual polymer strands between the cross-link point. And a lot of rubbers measured, if you check the literature, those are typically a few K. Apply into this equation. If this is like, say, 1,000, you know the density of the rubber, you know the R, you know the T, it will predict this is about 100 megapascal. Almost very close to the reality of what your rubber material would have in terms of modulus. So it's pretty successful in terms of getting the modulus at initial states. And I'll keep a sort of a secret and ask you guys to think about why in the large state of deformation this simple theory is not work as good. We kind of need to change a few terms to make it matches at large scale deformation. Okay, give you a little bit of thoughts while you are enjoying your Thanksgiving. All right, that will be it for today's class. Okay, early excited. Class is over. Have a good Thanksgiving.